I welcome everyone to this maritime innovation update on the topic of maneuver prediction for ships based on AI to support tracking applications. My name is Paul Koch. I will be the moderator for this session today. I'm working the team of maritime informatics together with my colleague Merk Yildiz, who will do the presentation. We're both working in data science and machine learning applications using AIS and big data. And he will guide you through this topic. Please remember that this whole presentation is recorded, and I'll ask you to switch off your microphone and camera during the presentation. If there are any questions, we will discuss them at the end. And with this, Mert, I'll hand over the microphone to you, so you can start with the presentation.
Thank you very much, Paul. As Paul already mentioned, today I will be presenting the intermediate results of our study on maneuver prediction for ships based on AI and also traditional methods. I must say that this study is focused on extracting maneuver points from AIS data, which is important for us due to several reasons. First of all, it is very useful for vessel trajectory prediction. There are different models. For example, there are different Kalman filters. Some of them are good for constant velocity models. Some of them are good for turning. And if one can understand the maneuvers correctly, then one can switch in between these models to do the trajectory prediction more accurately. It is also good for maritime anomaly detection. If a ship does a maneuver in a place that it is not supposed to do that, then we can understand anomalies from that. And it's also useful for maritime risk assessment. If a maneuver does something against the callback rules in a certain situation, then we can deem it risky. So now that I explained why maneuver extraction was mostly intertwined with most of our research, I will now talk about the methodology of this study. In this study, of course, the goal is to extract maneuvers from the AIS data, which means we want to say for a vessel a given AIS point if it is a maneuver point or not. So we chose 4 different methodologies. One of them is the simulation-based maneuver indicator estimation, which is a very straightforward and heavily exhausted method, which tells there is a threshold, and if your rate of turn is bigger than this threshold, then your ship is doing a maneuver. The second one and the third ones are 2 algorithms that we have created that use AIS data to do unsupervised learning to understand some kind of thresholds that we can use. And the last one is using the LSTMs for maneuver identification. And based on these 4 methodologies that I will explain you right now, in the future, we will develop a 5th methodology that will be a supervised learning model that will predict the closed form maneuver prediction functions, which you will see in the first methodology here. So starting with the simulation-based maneuver indicator estimation, I know there are too many visuals, but I will try to keep it as simple as possible. What we are trying to find is this X threshold, which says if a rate of turn is bigger than something degree per second, then that point is a maneuver. And in the perfect world where there is no sensor noise or no weather conditions, that X is 0. In order to create this equation, we did some turning experiments in the simulator. First of all, we did the turning circle experiments, and the second, we did the full S-turn crash test experiments. Here you can see the visualizations of them in latitude and longitude, what they look like. And we used these ship types that are given on the right side that covers a huge length and beam range, let's say. But we were, of course, bounded by the existing models in the simulator. But we hope to cover most of the range. And here are the closed form maneuver indicator prediction functions that we have come up with after investigating all the simulator dataset. We have found that the length of the ship itself is enough to understand, to take the threshold of rate of turn. So what this equation, for example, tells is when you put in your ship length in meters here, If your rate of turn in 15 seconds is bigger than the value given here, then your point is a maneuver. The same we have also for the significant speed change, where we extracted this data from the full ahead and full S-turn crash test. And again, if your deceleration is higher than the deceleration given by your length and this function, then it's a maneuver. And here are all the different functions that we have tried to come up with these final closed form maneuver prediction functions. These are all x's that we have tried. They are mostly based on length and beam. And all these x's are also used in polynomial functions up to 4th degree, and the best one has been chosen. The second one is the Gaussian mixture-based maneuver prediction. Here, our assumption is noise associated with heading readings follow a Gaussian distribution. Here, if you look on the right side, you will see a map of a ship trajectory. And on the right side, on the right of it, you will see the heading versus time. When the ship is going straight, the heading is along a line with a Gaussian mean. And there is, of course, some noise due to sensors and the weather. And we created an algorithm to extract these areas from the complete AS trajectory. It uses two parameters only, which are the maximum noise and the minimum length in seconds. The maximum noise is the amount of heading change between 2 points to be considered if it is a maneuver or a straight leg. If it is inside the noise, then it is considered a straight. If it is not, it's a maneuver. And the minimum leg is pretty straightforward. If the straight leg is found to be too short for, let's say, a vessel, then we disregard. This is a human-based parameter. And both of these parameters are trajectory or weather specific. And the third methodology that we used is we approached the whole maneuver identification process from a different point of view. Mostly people use the rate of turn and the heading. But what we did is instead we used the heading difference between consecutive points in an AS message, or let's say in a series of AS messages. Here, again, we assume the noise associated with heading readings follow a Gaussian distribution. And in the perfect world, where there is everything works perfectly, if you get the heading difference between consecutive points, what you will see is in the straight parts, you will have a zero change. And in the maneuver parts, you will have a change bigger than zero. But of course, since there is noise, there's a clear mean, but there is also some spikes around. And we defined an algorithm, we developed an algorithm which is based on Thompson methods that are heavily used in literature. We updated it a little bit using recursion to combine two different compounds together. And what this method does is one part of it finds these spikes, and the second part of it, based on the spikes, creates the maneuver around it. And the fourth method that we used is the long short-term memory networks. So before working in this, or let's say in parallel of working for maneuver identification, I was also working with LSTMs for doing trajectory prediction. And at the end of our studies, we have trained a very accurate LSTM that was able to perform the trajectory prediction of maritime surface vessels with mean accuracies of 40 meters in less than 10-minute predictions. However, there was a problem with the predictions, that it was not working very well when the ship was doing a maneuver. There was always an offshoot. And what we realized is there is an abundance of straight legs when you try to train a machine learning model to do trajectory prediction. Why? Because vessels simply do not want to do maneuvers. It causes more fuel to do maneuver, and it also decreases your speed, as we have seen in the simulator experiment. Therefore, it increases the cost. Therefore, they go straight. And when you train a machine learning model, it learns how to go straight pretty well, but not the maneuvers. Here on the bottom side, I gave you an example where we have the original trajectory, a random trajectory I sampled. And I am zooming into this part here. And here we have two different LSTM predictors. One of them is the one with yellow that predicts 4 steps ahead. And the one of them is the one with red that predicts 8 steps ahead. And as you can see, the blue one is the original trajectory. The 4th step predictor is very close to the actual trajectories, but the 8th step predictor is always doing an offshoot during the maneuver. And before throwing this model to garbage for not doing trajectory prediction very well, we decided to use it for maneuver identification. We extracted what are these offshoots during maneuver. By using unsupervised learning, we came with thresholds, and we used these thresholds to use this model to predict the maneuvers based on the offshoot. After we created all these models, of course, we also created the evaluation test set. What we did here is we get a human expert, which was me for this case, and I went through our AS data and extracted maneuver timestamps and also their heading differences between from the start and the end of the maneuver. And I did it for ships of different sizes. And then I tested all the methodologies on the test set given. We calculated as the metric we chose the precision, which is basically the detected maneuver points done by the leg extractor and over the total maneuver points that was found by the human expert. And in our test set, LSTM showed the biggest precision with close to 80%. And it got followed by the Gaussian and noise-based leg extractors. And the last one was the threshold-based leg extractor one. This was more or less expected because this threshold-based one mostly works with understanding the evasive maneuvers due to the simulator being in a very good, due to the tests that we did, like turning circle and pull-S turn are evasive maneuver actions. It was able to detect evasive maneuvers better, but from understanding day-to-day maneuvers, it was not working pretty well. On the left-hand side, you can see the performance comparison of leg extractors at different lengths of the ships. Here, most of the time, the graph is dominated by the LSTM-based leg extractor, but when the vessel length is increasing, the noise-based leg extractor showed better results sometimes. And on the right-hand side, we also check something else. As the human expert, I was giving the start and end timestamps of the test sets. And what we did here is we checked when the leg extractor chose which timestamp as the starting point of the maneuver. And based on that, we found out the time delay of maneuver extraction. And as you can see, for the most of the methods, it's always on the positive side. So the maneuver starts and leg extractor is able to find it, maybe in the next point or so. But for the LSTM-based leg extractor, the offshoot is actually happening before somehow from the data. And most of the time, the time delay is on the minus, which means that this method is actually predicting the maneuver. It will tell that the maneuver is going to happen soon. This soon is most of the time in between 150 seconds or so, but still it's a prediction which can be improved. And yeah, the possible use cases. Of course, the maneuver extraction can be used for helping traffic network extraction. As you know, people use distance-based clustering methods to the traffic network extraction. And since if we get only the maneuvers from all the trajectories, then the distance-based clustering would be much more simpler. Or the maneuver extractors, as I mentioned before, can be used for trajectory prediction. If you have different models that are focused on different ship motions, one for turning, one for going straight, these maneuver extractors can help you choose which one to use at a given time. And of course, the maneuver extractors can be used for encounter mining in AS. If a ship is doing an evasive maneuver so close to another vessel, then that can be used as a way to understand encounters. Here on the bottom side, you see one example that I extracted today from a random trajectory. The yellow ones are the maneuver points that we have found, and the blue ones are the original trajectory. That one was for a cargo vessel, but the developed algorithms are not specific to any ship type, so it can be used for anything. And with this, I will be concluding my presentation. I hope I was on time. And if you have any questions, feel free to ask them. You can either open your microphone to ask them directly, or you can write it to the chat. And yeah.
thank you, Mert, for the presentation. It's always a very interesting topic, and it has plagued us for quite a while now. So, as Mert already said, if you have any questions, you can just open the, or it's an open floor, so you can unmute your microphone and ask the question either directly or via the chat. And if there are no further questions, there is at least one from my side, which would be that in the beginning you mentioned 4 methods, but I think in the bottom of your slide there was a 5th, like AI-based approach, which probably goes beyond LSTMs. Could you elaborate a little bit on that?
Yes. So I must state that all of the methodologies that we have developed are based on, at least 3 of them are based on AS data, and 1 of them is based on simulator. But this AS data is from the same data source. We use the Danish Maritime Authority's AS data. So when people have different AS data sources that they have acquired from different bodies, then these algorithms will need adjustments depending on, let's say, the temporal resolution of the data or the spatial locations of the data. So what we are trying to do with the 5th method is we will try to create a closed form prediction function that's a base model, like the, let's say, it will be a long shot, but like GPTs, where people can fine tune it with their own data in the end to make it work based on their own AS. So the 5th method is still in development. It uses what we learned from here to give a closed form function with coefficients, basically for different data sets. I hope they answered.
Yeah, that's actually, I remember that we talked about this. I just wasn't too sure what you were mentioning with it in the presentation itself. So if there are any other questions, then now would be the last chance. If not, I can only recommend to look out on our website and LinkedIn channels for the next MIU. And I wish you all a nice weekend. You will find this presentation as a recording on our YouTube channel. And of course, if there are any questions afterwards, you can just reach out to my colleague via his mail address. Thank you very much. Have a nice weekend and see you at the next MIU.